Good day folks and welcome back. Today we're going to be creating our own spring tension landing gear lever. It sounds complicated, but I promise you anyone that is into flight simming can create this, and it can apply to other games as well. But it doesn't matter. Today we're going to be looking at flight simming landing gear lever. Is it just going to be a lever? No. It's also nice that if you have a little bit of a visual indication which gear is down, which landing gear is up, and if they're all up, etc. So we're going to be including the lever, the lights, and the logic behind it. Now before we get started, I want to say thank you to all the Patreon supporters. If you're interested in supporting the channel, go check out the link in the description down below. What's the easiest way to help the channel out? Hit the little subscribe button, hit the like button, and I want to say thanks to all of you who already did. Now, if we take a look at this unit, there are three areas that we can clearly differentiate. We got the master warning and master caution. We already did a video on this, so if you're interested in that, go check it out in the description down below. We've got an LED that says if the gear is fully extended, so for the nose, left and right gear respectively. And we got it says down, but it's meant to say up because it indicates if all gears are fully extended. And then we've got the lever. Now the lever can't just be moved up or down. See, it's blocked, so we need to pull it out and down, out, up. And that is how we're going to be creating this. We don't want it to be just a normal lever that's a little bit boring. We want something it has a little bit of a mechanical feel to it. So let's take a look on how you can create one of these for yourself. So here we got the model of the lever. It's pretty straightforward. For the encasing, we've got a case, speaks for itself. And I've printed a separate front because that would just make it easier to print in the details. Laying down. I just glued it on with some screws, etc. And we got the iconic landing gear. Is it called a knob? I always call it a knob, but I have to think about something else. That doesn't matter. Let's say that we take off the outdoor enclosure. Here we go. And let's hide not that one, the front. The front. Here we go. We are left with a contraption that looks like this. And the way it works is actually pretty straightforward. Now the moment we pull, it pulls, oh, it's locked, isn't it? Yeah, it is. But it pulls it out of this base a little bit, and then the springs pull it back, so it falls back into these locked in features. Now in real life it looks a little bit more impressive in my opinion. And when we put it together, I'm leaving the tape on to make sure that it's not scraping against the plastic when we pull it out. A, for the noise, and B, for the longevity. So I leave the tape on. Now I place the crossbar that will make sure that our lever stays inside our little guidance cutout. I put on the end caps, make sure that they're on there quite firmly. Before you put the end caps on, I'd highly recommend to attach the springs towards the caps, or else it's going to be quite a hassle to put them on post assembly. I speak from experience. Now we can clearly see that we've got some limit switches. I've glued them on with this amazing German glue brand. I'll put the link in the description down below. Now you could put in the LEDs through these holes that you see here, but the light would be A, very bright, and B, light just looks better when it's diffused. So you could just put in the LEDs into those little holes in the case, but it really wouldn't, it would look okay, but it wouldn't look great. Now I put a little recess in the outside of the case to accommodate a little bit of a diffusion plastic that I bought that is also used for lampshades. I've used it in many projects. You can just paste it on there, put on the front cover, and it will look stunning compared to just a plain LED. Now this piece could have used a little bit of sanding to get rid of those nasty layer lines on top, but I was actually quite satisfied with the result. If you want it to look more smooth, go apply some more sanding paper and work your way down up to something like 1500 if you want a really smooth one, 2000 even, if you're feeling rather adventurous. But if you're just like me, a good layer of paint and a clear coat will do just fine. If you're going to be using something like a spray paint, I highly recommend getting a pair of good respirators to make sure that your lungs will love you for years to come. Now the wiring of this device is actually pretty simple. We've got 4 LEDs and a limit switch. Now a limit switch, the name says it all actually, is basically just a normal switch, a push button, whatever you want to call it. It has 3 pins. You only need 2 of them to determine whether it's open or closed, because if that pin is closed, it means the other pin is open, and if that pin is open, that means the other pin is closed. So the techniques required are actually quite simple. Now, I could lay this out on a breadboard, and here we have our 2 LEDs, and we have a switch, and we've got a resistor, but it's going to be a little bit messy to understand, so I'm going to show you how it's wired using fritzing. Now, we've got a breadboard. Why do we need resistors? Pretty simple. If we don't add resistors, our LEDs will burn out the moment we put 5 volts through them. So to circumvent this, we add a resistor each, which limits the current that runs towards the LED, making sure that they don't burn out. Well, at some point they might burn out, but at least not instantly by our own wrongdoing. Now the switch and both LEDs each get their own dedicated line towards the board. Any digital pin or even analog pin will do. I'd recommend to skip the 0 and 1, but let's say 13, 12 and 11, or whatever pin you want to use. And if you take a look at our LED, they have 2 legs, the other one has to go to ground. Now you could run each wire to ground, but sometimes it can be tidier to connect the ground of multiple components together to reduce the amount of wires that get cluttered up in our design. So in our case, I've connected the first LED towards the ground of the second LED, towards the ground of the switch, and then at one point I run everything to ground. Now our project uses 4 LEDs and 2 switches, but the wiring stays the same, so you can just take the same approach, add a resistor for the LEDs, run one wire towards ground, the other one towards a digital pin on a board or any other pin, and you're good to go. Now coding up the landing gear lever is quite simple. If you have been following along with my other videos, this will perhaps even seem a little bit repetitive to what you already know, but if you're new to this, don't worry, we'll get you through this step by step. First of all, we have to include the Bits & Droids flight connector, which we do with the line include Bits & Droids flight connector.h, which you have to download from either my website or from the Arduino manager. Now, then we create an object for the Bits & Droids flight connector, which I just called connector. You can call it anything that you like. I like the word connector because then it's really obvious what the object does. It's a connector with the game, and we can apply all the logic that's inside that library towards this object. And then we have to initiate it. Now, this is a little thing that I already pre-filled. It's const byte up button, down button, front LED, left LED, right LED, lower LED. And the things that I've put in here are the pins of the board where each element is hooked up to. So my up switch is connected to A2 on my Arduino. Down switch is connected to A1 on my Arduino. The left for the LED for the left gear, right gear, and nose gear is 3, 2, and 4. And the lower LED indicating that the gear is up. I just realized that I've got down written on there. One thing that we need to include is a serial.begin 115200. What does this do? A serial is a way to communicate for our microcontroller with our PC over USB. Serial means that it sends zeros and ones in a straight line and a straight line back, and then it converts that to a message. If you really decode it, you need to start to learn some binary and stuff and learn how to decode these messages, but luckily the Arduino does all that for us. We have the PC application. We have Microsoft Flight Sim, which receives data, sends data towards the EXE, so the connector. The connector wraps all that data up, sends it to our board at a certain rate. So how fast the data flows over the line and how fast the data flows the other way around. Now 115200 indicates how fast it goes. And you have to make sure that everything matches up, so it reads at the same speed as that it tries to write, and vice versa. 6 elements: up button, down button, LED 1, 2, 3, and 4. But we need to tell the board itself that it are what those pins actually do. Because right now it can't read, so it doesn't know that we call it front LED. It can read that it's called front LED, but it can't deduct that now it's an LED, so it acts as an LED. So we see pin mode, front LED, comma, and it's going to be an output. Because we want to send the signal out towards the LED. We don't want to check if it's on or off. We say if something is true, turn it on. We don't say if the LED is on, do something. It could be done that way as well, but then we could get a little bit more of a complicated logic going on. So right now we're going to keep it simple. Talking about simple, 1, 2, 3, and 4. And now we just swap out front LED with left LED, right LED, and a lower LED. Here we go. Now the last thing that we need to do is the up button, which is going to be input underscore pull up. And we just copy this once again. Here we go, down button. Now what's input pull up? The moment we have a button, we have a toggle, when it's closed, it can flow from left to right, and the energy can go from the pin to ground or wherever it has to go. The moment the toggle is open, a signal is applied, but it has nowhere to go. It can't go back, it can't go forward, it gets all erratic, statically, you get wrong readings, it's a big mess. So what happens is that once we activate the internal pull-up resistors, a resistor is applied to the line going out. So the moment the toggle is still open, it still has a path to ground, and you get stable readings. The moment you close the toggle, path of less resistance, it can go over the toggle towards wherever it has to go. But if we don't define this, we're going to be having some trouble later on. You could also apply the resistors yourself in a circuit. This is just an easier way, in my opinion. Now the logic for the up button and down button is the same. It just has a little different command it sends out. So if the up button is triggered, we want to raise the gear. If the down button is triggered, we want to lower the gear. And the same goes for the front LED, right LED, left LED, and the other LED. The logic is the same for each LED. It just has a different cutoff point. We want one LED to turn on when the front nose gear is down. We want the other LED to turn on when the left gear is down, etc. But it's just a repeat of the same trick with a different trigger. So I'm going to show you how you can do it once, and then it's up to you to implement it for the other features. Now let's begin with the buttons. The way these triggers work is that we press them, but they stay pressed. So we can't check if the button is pressed, send the command. So what would happen is it would go into position. We would push the button in, but it would be staying pushed in. So we keep sending the command to raise the gear, which isn't really that big of an issue, but it's just not really that tidy. If commands comes in at the same time, it needs to go out. We occupy the serial line because it's a one-way street all the time. It's just really not that good of an idea. So if we don't check if it's pressed down, we need to check if the current state, so is it pressed or not pressed, is the same as the last state. Now we want to check that if we press it and the previous state was high, then we send the command. We don't want to send it when it's pressed, high, and the previous state was high, only when it's lower and the last state was high. So to do this, we need to keep track of the states. So we say Boolean, because it's a really small data size for our Arduino. So we say Boolean last up state. And we do the same, and And logic-wise, if you want to do it for the down button, you do just exactly the same. Last down state. Now, we're going to check if the current state is not equal to the last up state. I just changed this to up, by the way, because then we have a difference between the up and down button. If the current up state is not equal to the last up state, we know that something has changed. And then if the current up state is equal to low, here we go. Don't forget to say last up state is now the current up state. So in the next iteration of the loop, we check against the new default value. So if the button is pressed, we want in the next loop to cross-reference it from the pressed position and not from the erased position. So we say if current up state is low, what do? We say connector dot send. This is the up button. So we say send gear. I need to have a little bit of a sneak peek. Send gear up. And that's it. Now there is a little caveat. Now I get lots of comments all the time about this. It's a delay. Best practice is to have a timer in there, but it's going to be a really short sketch with not lots of moving parts except for the lever, a little bit of a lights going on and off. So a little delay can't hurt. Now why is the delay in there? The moment we press the button, what usually happens is the contacts bounce a little bit, it goes on, and off. And the last thing that we want to have is that the gear goes up, 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 up. So if we have a little delay of 50 milliseconds, more isn't really necessary. It sends the command when it closes and it doesn't trigger for the bounce period. Now, once again, our timer is going to be more tidy. It's going to be better for your code. The delay freezes up your entire CPU process. But for now, this will suffice perfectly. And that's it. This is all you need. Here we go. Landing lever up logic. I will put this up on my website as well, so you can look at this code, see if you can understand it, and then implement the same for the landing gear down. Exactly the same logic, we just changed the pin. We create a new variable for the old lower state. We check if the states are the same. If so, send gear down, set the new state to the old state, of the old state to the new state, and a little delay, and we're done for. And then you got all the logic you need already for the lever. Now the LEDs. Now for the LEDs, we need to do it the other way around. Now we check the physical object, so the lever, is it pushed into place? If that's the case, send a command. For the LEDs, we want to flip that. We want to see if the game has a variable that is beyond a certain threshold, turn on the LED. So now we're just going to reverse the logic and do exactly the same actually as the lever, except we turn something on instead of send something towards the game to turn something on. Now I always like to put this line at the top of my loop block, just because I got used to it. Connected data handling. Now this makes sure that once we receive data, it gets properly formatted, it gets stored in the library, and we can access the data. And I've just put it always at the beginning of the loop block, so I know where it is, I know it's in there, and I can't forget about it. Without this line, you can't retrieve any data. Well, you can, but then you have to implement the entire serial logic yourself to see what happens. Now, I'll show you the nose landing gear. The nose landing gear I want to retrieve as a percentage over 100. So from 0 to 100, which is going to be smaller than 255. Why is that relevant? Well, an integer has a max value of 32,767, which takes up more space than a byte. A byte has a max value of 255, but it just consists of 8 zeros and ones. So if the first 0 is a 1, it's a 1. If the second one, it's 2, 4, 5, 8, 16, 32, 64, 128. And with those numbers, you can turn one on or turn the other off to get all the numbers in between 0 and 255. But it's a really small package, so if it's smaller than 255, I'd recommend to go with a byte. Now, percentage is always smaller than 255, so that's fine in this case. I say this, but remember that sometimes, like the flaps, it has a negative value, so 0, 80% and raised 80%. So check for yourself if it doesn't cause any issues with a byte. Then an integer might be more appropriate. So we say byte. Current gear level is going to be connector.get. Now I've got a peek at my own documentation, all the code that I've already written. Get gear center position percentages. Here we go. And there is also, you know what? Here we go. I'm going to put them all in. I'm going to call them a little bit differently so you know which ones you need to get. Front gear, left gear, right gear. Connector.get gear position %, get gear right position, and center position. I see I got the same one twice, so I messed this up properly. This is get gear right position %, and then this is going to be get gear left position %. Now all of these return a value between 0 and 100. So if front gear is going to be bigger than 98, what do we want to do? We want to digital right. We called it front LED, I believe. Did we? Yeah, we did. I want to put it high. Here we go. Else digital right front LED. And we're going to put it low. Now, why did I pick 98%? It's that some planes in the game actually lower and raise the gear towards a 99% value or something like that, and then you get some kind of issues where it isn't always at 100% or it's 99.99997. It's just easier to take a cutoff point like 98, then it's almost lowered to the max, but it still always triggers. Now you could do this. Another thing, if you don't like this, is digital right front LED. And we say front gear is bigger than 89. Now you've got one line. This is a true or false statement. So it returns true or false, 0 or 1, or 1 and 0, true or false, yeah, 1 and 0. High and low in the backend are also 1 for high, 0 for low. So if front gear is bigger than 89 is false, this will be 0, so low. If it isn't, it's going to be high, it's going to turn the LED on. And that's basically it. If you just repeat the same logic, you know, this is so simple. I'm just going to do it like this. I said I'll only show you once, but here we go. Done. You got the landing gear lights going on or off depending on the state. And you got your front gear, left gear, right gear logic. Now we already got a logic for the lever. You can just copy and paste that same logic for the down position. This is all you need for the LEDs. I said I'd only do one LED, but I already gave away 3 of them. So I'm going to leave it up to you to implement the red LED at the bottom that turns on when everything is raised. It's an if statement that you're going to be using probably to check what the state is of these auto variables. And if it's beyond a certain threshold, turn on that LED. So it's quite a short piece of code. I'm going to also put this on the website and a link in the description so you can read up on it for yourself. Now, I want to thank all of you for watching. If you haven't already and you like the content and want to see more of it, don't forget to hit the subscribe button somewhere in this region. There's also a like button if you want to. Thanks for all the Patreon supporters that make this possible. And most of all, I hope to see you in the next one.